Welcome to Yatim Khana and Madrasa Anjuman Khairul Islam's Pune College of Art, Science and Commerce Camp Pune 1. Myself, Dr. Arif Tamboli, working as Associate Professor in the Department of Electronic Science. Today we are going to study the second part of a Schmitt trigger, that is non-inverting Schmitt trigger. In the previous lecture, we have completed inverting Schmitt trigger designed by IC741, that is operational amplifier. In today's lecture also, we are going to design non-inverting Schmitt trigger again by using IC741, that is operational amplifier. As you are aware that Schmitt trigger is also called as sine wave to square wave converter. It converts sine wave into square wave, and the frequency of the square wave at the output and the frequency of the sine wave at the input are same. So let us proceed for circuit diagram of Schmitt trigger and non-inverting Schmitt trigger. So this is our circuit diagram of non-inverting Schmitt trigger. Observe the circuit diagram very carefully. You will observe that as the name suggests, non-inverting, the input voltage, that is a sine wave, is applied at positive terminal of the operational amplifier. So Vin is applied at positive terminal, but it is applied through the resistor R2 and feedback resistor is R1. So here you might feel that why this is called as R2, why not R1? And why this is called as R1 and why not R2 or RF, you can say, because it is always used as feedback resistor. So I will explain you the logic behind this and they will understand in a very simple manner. See now, look at this diagram. This diagram is again same non-inverting Schmitt trigger. But in this diagram, what is done? This minus terminal upper side plus terminal lower side. We are not using inverting input terminal in non-inverting Schmitt trigger. Therefore, when we are not using inverting input terminal in non-inverting Schmitt trigger, it is to be grounded. And same thing is done here also, but only in this diagram plus sign is upper side, means non-inverting input terminal upper side, inverting input terminal is lower side. So here it is not used, that's why it is grounded, because the name of our circuit is operational Schmitt trigger, non-inverting Schmitt trigger by using operational amplifier. So now here the diagram is looks to be more simple, because in this case inverting input terminal is grounded straight away like that, and here plus sign is there, and this is the two resistors. Now try to understand why this is R1. When we studied inverting Schmitt trigger at that time, we know that as the name suggests inverting Schmitt trigger, we applied the sine wave at inverting input terminal. We applied the sine wave at inverting input terminal directly, and this potential divider circuit was there. This was upper resistor R1, this was lower resistor R2, and this terminal was grounded. This terminal was grounded, and this point was our X point where Vx voltage was given to the same terminal. Only the thing is what, in case of inverting Schmitt trigger, this inverting input pin is used to apply the input voltage Vin, that is a sine wave. Now, as the name suggests, non-inverting Schmitt trigger. So, non-inverting Schmitt trigger means inverting input pin is not used, that's why it is grounded. And non-inverting Schmitt trigger means input is applied to non-inverting input terminal and potential divider circuit remains same. So, this is upper resistor, this is lower resistor, and therefore we are not going to change the nomenclature of resistor. This resistor is R1 only, this resistor is R2 only, which we have used in potential divider circuit as upper resistor and lower resistor. Only the thing here, this point is Vx point. It is again applied at non-inverting input pin, but input voltage V in sine wave is applied at the input terminal through the resistor R2. So this is the change, and therefore you can take this diagram or you can take this diagram. So now you might have been understood that why R1 is here and why R2 is here. So here this R1 and R2 are potential divider circuits. So this diagram is shown R1 and R2 on upper side. If you take this entire diagram on the lower side and if you shift this negative terminal on upper side, the diagram becomes simple like this. But we are going to use this diagram. You please remember this diagram, that input voltage is applied to non-inverting input pin because our circuit is non-inverting Schmitt trigger. Potential divider circuit is as it is. Inverting terminal pin is not used, therefore it is like that. Now again look into this diagram. Whenever you apply the input voltage V in sine wave, whatever amplitude and whatever frequency, here R2 is the first resistor through which the input signal gets applied to the op amp at non-inverting input pin. And this is the point A, which we called, that is the junction point now. Here this junction point is connected to the feedback resistor R1, and then when input current In starts flowing through R2, because we are applying input voltage over here, when input current In starts flowing through R2, that input current will come to the point A, and as all you are aware that input resistance of op amp is in mega ohm, very high. Therefore, very negligible current flows through terminal A to the inside the op amp, and 99.99% current gets diverted to the feedback path because output resistance of the op amp is very low. It is in few ohm, and because of this it is said that the total input current In when it comes to the point A, out of that 99.99% current goes to the feedback path and like this In. Therefore, this In is actually a feedback current, but If is equal to In. If is equal to In. Therefore, instead of writing If feedback current, we write here In only. So this current and these currents are almost same. And in this way, one more concept is here. In operational amplifier, this point is called virtual ground and voltage at this point is always 0 volt. So in this way, you try to understand this diagram. It is a very simple, and after this diagram, we will proceed for understanding the non-inverting Schmitt trigger, that is understanding of hysteresis voltage VH, how to derive that, what is the output of this circuit. As it is a Schmitt trigger, it is a sine wave to square wave converter, therefore no doubt that the input sine wave which is applied here will get converted into a square wave and will appear over here. The frequency of the input sine wave and output square wave will be same. That is to be remembered. So it is a non-inverting Schmitt trigger, means sine to square converter. So output is a square wave. Now only the point to be understood that where is upper trigger point and where is lower trigger point, and upper trigger point voltage and lower trigger point voltage, how to calculate that, and which component decides the upper trigger point voltage and lower trigger point voltage. So it is also very simple that only two components are there in this circuit, namely resistor R1 and R2. Therefore, no doubt that the upper trigger voltage as well as lower trigger voltage is also decided by these two components, and these two components if you change, then you can change the upper trigger voltage and lower trigger voltage, and therefore it is also said that the hysteresis width is also decided by these two components only, namely R1 and R2. So let us proceed for that. This is the symbol of non-inverting Schmitt trigger. So here this is the hysteresis loop which is shown. Here triangle is there because we are using the op amp, and here no bubble sign, that is called your non-inverting Schmitt trigger. Now normally in case of non-inverting Schmitt trigger, initially the output of non-inverting Schmitt trigger circuit is in low voltage level. So it is exactly opposite to the inverting Schmitt trigger. All of you have understood that in inverting Schmitt trigger, initially the output is in HVL, high voltage level. Accordingly, you have to understand that here, initially the output of non-inverting Schmitt trigger circuit is in low voltage level. Therefore, you will understand from this graph, which is self-explanatory, that we are applying an input signal V in, which is a sine wave, and this sine wave is having a peak voltage of plus 12 volt positive peak and peak voltage of minus 12 volt as a negative peak. Now, as we have cleared that, initially, the output voltage Vout of non-inverting Schmitt trigger is in LVL, low voltage level. This here, the graph x-axis is the time, y-axis is the voltage. So initially, I have shown the output voltage as LVL below x-axis, and this LVL is equal to minus 12 volt. So this is basic understanding. In case of non-inverting Schmitt trigger, initially the output remains in low voltage level, and low voltage level is equal to minus 12 volt, or low voltage level is equal to minus VEE. So in this way, this is the state. Now the question comes, the LVL changes its state from LVL to HVL, and when does it changes the state? So the concept is very simple. When sine wave is in progressing in the positive half cycle and it starts from 0 volt, then the voltage goes on increasing from 0 volt to 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, and 6 volt. So here we have taken 6 volt as upper tripping point. So UTP, upper tripping point, LTP, lower tripping point. So here this voltage is plus 6 volt we have taken as a upper tripping voltage. Therefore, when the sine wave crosses the 6 volt level, the output of the non-inverting Schmitt trigger changes its state from LVL to HVL. Changes its state from LVL to HVL. And then when sine wave goes above 6 volt, HVL will continue to remain, and HVL will continue till the sine wave does not goes below minus 6 volt. HVL will continue to remain till the sine wave voltage does not goes below minus 6 volt. So the HVL will remain from plus 6 volt portion of the sine wave to the minus 6 volt portion of the sine wave. And in this way, this is the time duration for which HVL remains there. When the input voltage of the sine wave just crosses minus 6 volt, the output of non-inverting Schmitt trigger changes its state from HVL and goes to LVL, and it will remain in LVL from minus 6 volt of the sine wave and to the plus 6 volt of the sine wave. So in this way, time duration of LVL is from minus 6 volt of the sine wave to the plus 6 volt of the sine wave. So in this way, this is the explanation about that. Now this cannot be understood very clearly from the circuit diagram, because in this circuit diagram, at a point A, two voltages are acting. One voltage is input voltage sine wave in this direction from left to right, and another voltage is output voltage square wave in this direction from right to left. So in this way, at a point A, two voltages are acting. One is the sine wave from left to right, another is the output square wave from right to left. Therefore it becomes very difficult. Therefore it is explained with the help of graphical representation only. How does the output square wave changes? And it depends, the change means trigger point depends on what? Trigger point depends on values of R1 and R2 that we are going to study. Now what is the hysteresis voltage? So hysteresis voltage is again a graph similar like that. It is x-axis, it is y-axis. So hysteresis is a graph of output voltage on y-axis, output voltage on y-axis, and input voltage on x-axis. So in this graph, on both axes, there is a voltage only. So output voltage of the op amp is always swing or changes from plus Vsat to minus Vsat. output voltage of the op-amp always swings or changes from plus Vsat to minus Vsat. Plus Vsat means plus VCC, minus Vsat means minus VEE. And resistor R1 and R2 are very much important because they plays the role in deciding the upper trigger point and lower trigger point. Upper trigger point means UTP, lower trigger point means LTP. The values of R1 and R2 are deciding this voltage VUT, upper trigger point, and this voltage VLT, lower trigger point. So in our example, our upper trigger point we have taken as a plus 6 volt. So it is on the right hand side of the 0 on x-axis, and minus 6 volt is our lower trigger point. So it is on the left hand side of the 0 on x-axis. And in this way, this width of the hysteresis can be changed, and we are going to derive the equation for hysteresis voltage, that is called VH, in case of non-inverting Schmitt trigger. So this is a very simple diagram. Now, what is the symbol of non-inverting Schmitt trigger? Symbol of non-inverting Schmitt trigger is a triangle because op-amp we are using. There is no bubble because it is a non-inverting, because we are applying the input to the non-inverting input pin, and this is the symbol of hysteresis. So this is there. Now what is the application of this circuit? Here it is very simple. For non-inverting Schmitt trigger, if we apply the input square wave which is having positive edge, so change in the voltage level from LVL to HVL is called positive edge. This positive edge is little bit inclined. It is not exactly perpendicular. It is little bit inclined. It is not exactly perpendicular. Therefore, here this type of inclination is removed at the output of non-inverting Schmitt trigger, and this positive edge will appear over here exact perpendicular. Secondly, whenever the level changes from high voltage and goes to low voltage, means this HVL goes from high voltage level to low voltage level, that is marked by the negative edge, that is marked by the negative edge or downgoing arrow. And here you can see this downgoing arrow or negative edge is also having some inclination. It is inclined, it is not a perpendicular exactly. And this also a problem which is removed in at the output of non-inverting Schmitt trigger. So negative edge will also appear exactly perpendicular, and in this way it is said that non-inverting Schmitt trigger gives the proper shape to the input signal, and there is no change in the frequency. It gives proper shape to the input signal. The frequency will be the same. So in this way here, this is called your non-inverting Schmitt trigger. Same functioning is there for the inverting Schmitt trigger, but in non-inverting Schmitt trigger, HVL remains as a HVL. LVL remains as a LVL. There is no change in the HVL and LVL in case of non-inverting Schmitt trigger. In case of inverting Schmitt trigger, there is change in the levels of the 180-degree phase. Now let us proceed for the derivation of hysteresis voltage VH. So it is a very simple derivation, because in this derivation, basic concepts of the operational amplifier are used, which I have already told you that whenever you apply the input voltage V into the op-amp through the resistor R2, due to input voltage V in, input current I in starts flowing. When that current passes through R2, it comes to the point A and it tries to enter into the op-amp, but input resistance of op-amp is in mega ohm. Therefore, very less current goes inside op-amp, and maximum current gets diverted to the feedback resistor. Here we have considered this as a R1 resistor, and current goes to the output because output resistance of op-amp is less, it is in ohm. So now let us proceed for the derivation of hysteresis voltage VH. I have taken the same diagram over here because we are applying some basic laws such as Ohm's law, Kirchhoff's current law, potential divider logic, and we are finding the output voltage here, over here. So that output voltage will be calculated, and according to that output voltage, the upper trigger point and lower trigger points potentials will be decided. So let us see now. In above diagram, consider operational amplifier does not absorb the current. So we will consider that input resistance of op-amp is very high. It does not absorb the current. Therefore, whenever input current In passes through the R2 and comes to point A, 99.99% of the current means same current goes to the feedback path. Therefore, current flowing through R2 and current flowing through R1 are same. And by using Ohm's law, that is called V is equal to I into R, we can write In is equal to. Now this In you want to calculate, you know the voltage, you know the resistor, so V is equal to I into R if you use. So In is equal to V in divided by R means R2. Here resistor R2 will come, and this is our equation number 1 using Ohm's law for the current flowing through R2. So we have used Ohm's law here for the current flowing through R2. V is equal to I into R. So here In equal to V in divided by R2. Very simple equation. Then we'll proceed next step. We want to calculate now the current flowing through R1. Now the current flowing through the R1, when we are going to calculate, we are using a very simple logic of what here this point is A, where there is a VA, voltage VA is there. Here there is one point where there is a voltage V out. Now this is the R1. Whatever the value of R1, on the left hand side of R1 there is a VA, on the right hand side of the R1 there is a V out. And you know that if the potential difference, between VA and V out is maximum, then large current will flow through this. And if the potential difference between VA and V out is minimum, then less current will flow this. Potential difference means what? Let us see here. So this point A is VA point, R1's left hand side is VA, R1's right hand side V out. Suppose our VA is having a potential, suppose 1 volt, and here it is having a potential, say suppose 5 volt. So here 1 volt and here 5 volt. So potential difference is minus 4 volt. But now suppose VA is at 10 volt and V out is at 1 volt. Potential difference is 9 volt. So depending on this, the potential difference, the current flowing through the R1 is decided. And therefore we'll use the logic to calculate the current through the R1, that is In only. That current is In only. But here the logic we are using is not Ohm's law, it is a potential difference. So what we'll do here, VA minus V out will do, means that is the potential difference, and we'll use the resistor value R1 and we'll calculate the current In. So the logic is what's here, the potential difference VA minus V out, VA minus V out into the bracket, and I is here input current divided by R1, because if I take this R1 over here, so potential difference V is equal to I into R, that is R1 into In. So this is a very simple logic which I use over here to calculate the current flowing through the feedback resistor R1. So potential difference divided by value of resistor equal to the current, using potential difference logic for current through R1. So these two equations we got it. Now in the equation number second, VA is nothing but virtual ground, because this point of the op-amp is always a virtual ground. So here in case of op-amp, VA is equal to 0 volt virtual ground. Therefore, in equation number 2, we can write VA is equal to 0 volt, and you will get the value of this equation as In equal to minus V out divided by R1. Now look at the equation number 1, which we have derived by using Ohm's law. Equation number 1 represents input current In. Equation number 3 also represents input current In. But in equation number 1, the logic of Ohm's law was used. In equation number 3, the logic of potential difference was used. Doesn't matter, but both the equation represents same thing, means input current In. Therefore, in mathematics, it is said that both equation number 1 and 3 we can equate. So equating equation number 1 and 3. So equation number 1 I have written on left hand side. Equation number 3 I have written on right hand side. So V in divided by R in equal to minus V out divided by R1. Remember, this is a minus sign because here VA minus V out. VA minus Vout. Therefore, when it is 0, it is minus sign remains there. So this is equation number. Now we are going to just rearrange the terms left hand side and right hand side. So V in will keep it here only. This R2, V in divided by R2 it is there. So this I will take into the bracket, and then this R2 I will multiply it here. So star into R2, and then I will take this inside the bracket, and then V in is equal to minus V out, therefore multiplied by minus V out multiply star into bracket R2 divided by R1. So this is a simple mathematics, and in this way we got the magnitude for input voltage V in, which is equal to minus V out into R2 divided by R1. And from this magnitude only you can calculate the output voltage as V out equal to minus V in into R1 divided by R2. So in this way here, this is the equation for V in. This V in is the input voltage. This V in is the input voltage which is acting at a terminal A, which is acting at a terminal A. And this input voltage at which the output changes the state. So when the input voltage is equal to minus V out into R2 divided by R1, at that time operational amplifier changes its state from LVL to HVL, because in case of non-inverting Schmitt trigger, initially the output is in LVL. So this is the input voltage at which output of operational amplifier changes the state from LVL to HVL. Therefore, this is called your VUT, means upper trigger voltage. Therefore, this is called as VUT, means voltage of upper trigger. So, upper trigger point voltage is VUT is equal to minus Vout into R2 divided by R1. So, in this way here, this is the change in the state takes place from LVL to HVL, and this voltage is called upper trigger voltage VUT, upper trigger voltage VUT. Now let us go to the next. So up to this I think so Ohm's law, potential divider and everything is there. So this is the input voltage at which, because input voltage is sine wave going in positive half cycle, going in negative half cycle. So this magnitude of input voltage changes the state of the op amp from LVL to HVL, and that is called VUT, means upper trigger voltage. Now, but in case of non-inverting Schmitt trigger, initially the output is in LVL. Therefore, this output V out, initially it is in LVL. So LVL means what? Low voltage level, which is equal to minus VEE, which is equal to minus Vsat. Therefore, here if I substitute V out equal to minus Vsat, then our problem will get solved. So here we'll substitute V out equal to minus Vsat, because in case of non-inverting Schmitt trigger, initially the output is in low voltage level. Therefore, for this V out, we can substitute minus Vsat. Therefore, upper trigger voltage VUT is equal to, this minus sign will remain as it is minus over here. So this minus sign will remain as it is over there. Only V out will substitute as minus Vsat into, star means into, bracket R2 divided by R1. Now all of you know simple mathematics, minus minus will become plus, and therefore VUT is equal to plus Vsat into R2 divided by R1. And in this way you got succeeded in calculating the value of upper trigger voltage with the help of resistor R2 and R1 and Vsat, because Vsat is equal to plus VCC and minus Vsat equal to minus VE. You know the supply applied to the op amp, it is plus minus 12 volt or it might be plus minus 15 volt. So if you know the value of Vsat plus and if you know the value of Vsat minus, you are deciding the value of R2 and R1, and you can design the value of upper trigger voltage. So upper trigger voltage is equal to plus Vsat into R2 divided by R1. And in this way, if you got the value of upper trigger voltage, the lower trigger voltage is exactly same, but only instead of plus Vsat, it will come minus Vsat. So VLT, lower trigger voltage. VLT, lower trigger voltage, is exactly opposite of that. Instead of plus Vsat, it is minus Vsat R2 divided by R1. Now your job is 90% done because you got V upper trigger, V lower trigger means upper trigger voltage and lower trigger voltage. And what is hysteresis? Hysteresis is nothing but difference between upper trigger voltage VUT and lower trigger voltage. So let us proceed for that now. So here you got these two values VUT and VLT. But hysteresis voltage is equal to VH is equal to upper trigger voltage minus lower trigger voltage. Therefore, VH I will take over here. VUT upper trigger voltage you know very well, here it is VUT plus Vsat into R2 divided by R1. So we'll write here VH is equal to plus Vsat into R2 divided by R1. Now here minus sign. So here minus sign into bracket VLT, and VLT you know VLT is opposite of VUT. So minus Vsat into R2 divided by R1. So we have taken this into bracket minus Vsat into R2 divided by R1. R2 divided by R1 is round bracket complete, and this is one more bracket. Now, this equation, if you understood, in which VUT and VLT are substituted by using this equation and this equation. Now, minus minus will become plus. So, in this way, that minus minus will become plus. And here, when you say that this minus minus is plus, then Vsat plus, and this is again Vsat plus. So, in this way, 2 Vsat will come, and then 2 Vsat will be multiplied inside the round bracket, and it will come to 2R2 divided by R1 into plus Vsat. So this is a simple mathematics. Minus minus will become plus. So this is plus Vsat into R2 divided by R1 plus Vsat into R2 divided by R1. So it is 2 Vsat, and 2 will go inside the round bracket. So 2 times of R2 divided by R1 into plus Vsat. Or if you want Vsat on left hand side, you can write this plus Vsat into 2 times of R2 upon R1. Now this is the derivation for hysteresis voltage of non-inverting Schmitt trigger. It's a very simple steps. Now we'll just compare the hysteresis voltage of inverting Schmitt trigger and non-inverting. So I have written here for inverting Schmitt trigger, the hysteresis voltage VH is again almost same, only slight change is there. Plus Vsat is here, plus Vsat is here, into bracket. In case of non-inverting, 2 times of R2 divided by R1, and in case of inverting, 2 times R2 divided by R1 plus R2 divided by R1 plus R2. So here R1 plus R2 is there only, and that is the difference. But remember that a very important thing is what? A very important thing, when you draw the diagram of non-inverting Schmitt trigger, R1 should be here only and R2 should be here only, because this R1 is the upper resistor of potential divider circuit in inverting amplifier. This R2 is the lower resistor of potential divider circuit in inverting amplifier. We are not going to change the location of R1 and R2 neither in inverting Schmitt trigger or nor in non-inverting Schmitt trigger. So if you change these locations, then your entire equation will change. So please make sure that R1 is here only, R2 is here only if you are drawing the circuit diagram of non-inverting Schmitt trigger. And when if you are drawing the circuit diagram of inverting Schmitt trigger, normally for inverting Schmitt trigger, this R1 is over here as a potential divider circuit, R2 is over here, and then that is a very simple thing. The junction goes to the point B, here inverting input pin. So non-inverting input pin in that case. So in this way, hysteresis voltage is very simple in that case. Now, as I told you in the previous lecture, I am going to explain you some ready-made IC available in the market. In electronic market, some ready-made ICs are available, and that ICs are of inverting Schmitt trigger as well as non-inverting Schmitt trigger. So let us go to the 74LS14. So 74LS14 is 6 inverting Schmitt trigger. So why 6 it is called? Because inside that IC there are six inverting Schmitt triggers. So that IC looks like somewhat like this. Okay. So in this way, this, and there are 6 inverting Schmitt trigger. So one Schmitt trigger, whether it is inverting or non-inverting, is having one input and one output. In this way, 6 Schmitt trigger will have 6 inputs and 6 outputs, means 12, and 2 pins are for supply. So in this way, overall number of pins are 14 pins. So 14 pins are used. So ground is pin number 7, VCC is 14. Normally in case of IC, diagonally ICs pins are used for power supply. So this is one IC which is used as inverting Schmitt trigger. Now there is one more IC. The same IC is shown with the help of internal diagram like this 6 and this is 6. And what is the inverting Schmitt trigger? If input A, here see, input A, output Y, input A, output Y. For each Schmitt trigger, it is inverting, input A, output Y. If A is 0, Y is 1 because it is inverting. If A is 1, Y is 0. But it is a Schmitt trigger because inside this is a not gate. So inside the NOT gate, what is shown? Hysteresis is shown. So that's why it is said Schmitt trigger. Now in market there are other ICs also in which there are only two inverting Schmitt trigger. This is one and this is one. So how many pins will be required? Two pins for this input and output, two pin for this input output, and two for power supply. Or only six. So like that there are various ICs available. So this is a 7014 uh, inverting Schmitt triggers. Now this is one self-explanatory diagram. You know one NOT gate. This is a NOT gate. Here there is no, inside this triangle there is no symbol of Schmitt triggers hysteresis loop. Therefore it is a NOT gate. So one NOT gate, if you connect to another NOT gate, then that will become A is equal to Y. So in this way here one inversion, and then here A input, if I apply A bar and then again A bar A. So A equal to Y. In the same case, if you talk about inverting Schmitt trigger, if you apply the input A at the output of first inverting Schmitt trigger, it will be A bar. And if this A bar, if you apply to the second inverting Schmitt trigger, so A bar will become A bar and bar A. So this is the same thing, means this diagram will explain you that inverting Schmitt trigger 2, if you connect to each other, it will work as non-inverting Schmitt trigger. That is important. If you connect two inverting Schmitt trigger to each other, that is equivalent to one non-inverting Schmitt trigger. So it's a very simple. So there is one more IC 74HC 7014 hex non-inverting precision system. So here now see here, it is a hex non-inverting. So this is a non-inverting hex. Already we have studied here hex inverting. So this is your 74LS14 hex 6 inverting Schmitt trigger. 6 means hex. And here you can understand this very simple. Hex non-inverting precision Schmitt trigger. So let us see what is this. So see here 74HC4050. There are pin connections of the IC, and see this here symbols. So here no bubble. So like that. So it's a very simple. And in the similar manner in market there are other ICs. So here symbol of hysteresis, symbol of triangle, but not gate, means what? Not bubble, sorry. So means what? It is a non-inverting Schmitt trigger. It is a non-inverting Schmitt trigger. How many? There are three. So in this way, three inputs, three output, and two pins for supply. So it is a 8-pin IC. So here it's a very simple. You will get in electronic market non-inverting Schmitt trigger in one IC as a only one. In one IC as a only one. So one input, one output, one power supply plus 5 volt plus VCC and ground, and one is NC not connected. It is a 5-pin IC. So like that it is used. Then there is one more IC, it is called 74HC T2G17GV. So here dual non-inverting Schmitt trigger. Dual non-inverting. Dual means two. In this IC there are two non-inverting Schmitt triggers. So here you can look at this IC. How many pins? 3 pins on this side, 3 pins on this side. Why 6 pins? Because two non-inverting Schmitt trigger. One non-inverting Schmitt trigger will have one input, one output, like that. Two will have two input, two output, 4 pins like that, and 2 pins for the power supply. So simple logic. And this is the diagram of that internal diagram of that IC. It is having pin number 1 as the input of first Schmitt trigger, which is non-inverting, and pin number 6 as output of first Schmitt trigger. Here, pin number 3, input of second Schmitt trigger, which is non-inverting, no bubble here, but inside the triangle symbol there is a hysteresis, and this is the output, pin number 4. So you will understand that here pin number 2 and then 1, 2, 3, 4, 5 is not there. So pin number 2 and 5, definitely pin number 2 and 5 are used for power supply. Now the last one application is there, that is most of the time the Schmitt triggers are used to convert sine wave into square wave. So here you have to apply the supply, and then sine wave will be converted into a square wave. So this is the 74HC14. This Schmitt trigger is inverting Schmitt trigger because at the output there is a bubble mark. And in this way, I will conclude that you have understood the non-inverting Schmitt trigger in a very detailed manner, and I hope you'll remember the circuit diagram of non-inverting Schmitt trigger. Only don't change the position of R1 and R2. R1 will be used as a feedback resistor. R2 will be used as an input resistor, because R1 and R2 are used in inverting Schmitt trigger as potential divider circuit. And here again it is used as a potential divider circuit, but in this case, at the junction point A, two voltages are acting simultaneously. One is input voltage V in sine wave from left to right. Another is the output square wave generated V out from right to left. And therefore, while deriving the hysteresis voltage, what we have taken the help? We have taken the help of parameters of the op-amp. We have taken the help of Ohm's law. We have taken the help of potential difference logic. And in this way, the hysteresis voltage is calculated in case of non-inverting Schmitt trigger very systematically. I hope you have understood this, and with this we'll conclude that today we have completed non-inverting input Schmitt trigger, and in previous lecture I have also completed inverting Schmitt trigger along with derivation of hysteresis voltage. So thank you very much for watching the video. If you have any problem, again watch the video, go to the re-recording, and then you can watch the video a number of times. If you have any doubts, we are there to discuss with you. Thank you very much for watching the video.